Okay, everyone, so we talk about normal today. So what is a normal distribution? This, like, normal is same as like binomial, like it's a special name for distribution. Binomial is a special distribution in discrete random variable. Then normal distribution is a special distribution in the continuous random variable. So this one is a special one for continuous. Okay, why is special? Okay, you can think about why binomial is special. Because it's follow a particular like order, like you do n trials, and then every trial like it's got some patterns, like we have some patterns for it. And also the most important thing is we have this special way to find mean, variance, standard deviation. Mode is kind of the same way, but we can use calculator. But for mean and standard deviation, we have a special formula to do that. So that's why it's special. Then for normal, I said it's special, then it must be very special to think about the mean and standard deviation as well in this question, in this type of distribution. So what is a normal distribution? So the random variable x is normally distributed. This is the notation. Remember when we do binomial, we have a similar notation here, but instead we write bi here, like that's the binomial distribution with n comma p, like x is binomially distributed with n comma p. For normal, it's very, very interesting. The two parameters decide the normal is the mean and standard deviation. So the mean and standard deviation, you don't really need to find them. It's given in the distribution already. So I will say the height of 16-year-old girl is normally distributed with a mean of 160 centimeters and a standard deviation of 2 centimeters. So that's what I will give you in the question normally. Okay, that's the first type of question. And you can put that under this notation. Okay, you know x is normally distributed, so you say x is normally distributed. The first spot is the mean. The second place is actually the variance. So it's sigma squared, okay, sigma squared, the standard deviation squared. So what you put in the bracket is sigma squared, where the probability density function for x is given by that. Okay, a fantastic equation. Have a look at that. Well, you know what our density function looks like, right? Like before we have, if I open another one for you in the chapter 15. Well, that can be my density function with quadratic, and domain is -1 to 1. Okay, so it's a very simple density function. But now, unfortunately, we have a very complex one. So if I have a density function looks like this, then it is called a normal distribution. Okay, then it calls a normal distribution. No one really asks you to write down the normal distribution for me. No one will ask you this question. But I think you better remember that. Okay, you better remember that. You can put in the notes. Okay, you can have a look at it. Because we will talk about something else later. So if we can look at this, it's 1 over the standard deviation times square root 2 pi. Okay, so this place is my sigma and my mu is involved in this density function. Okay, this, or I can say the density function reflects my mean and standard deviation, So what I have then is an exponential to the power of -1/2. Okay, -1/2, x minus mu divided by sigma over 2. When I know my mu, when I know my sigma, then I can have a unique density function. Okay, I can have a unique density function. Also, we can see all of that, they are in charge of dilation from the y, dilation from the x, and horizontal movement, right? Like 1 over sigma, that's dilation on the from the x-axis, then divide by sigma and the x is dilation from the y, and x minus mu is horizontal movement, left or right, depends on the mu value. So they're not going to change the basic shape of the graph, but they will change like the dilation, like fatter or taller, or move to the left, move to the right, but the basic shape keeps the same. So when we sketch it, we can sub any value in. For example, standard deviation equals to 2 and mu equals to 5. If I put values in and I put in calculator and sketch this graph, the shape of this normal distribution is called a bell-shaped curve. Okay, it's a bell-shaped curve. So what's a bell shape? That's the bell shape. And our set, it should have this shape. Okay, when I put your value, like how many people, frequency, and blah, blah, the marks, I should have a curve like this. And then the top 0.2%, top 10%, top 50%, and then keep going that way. So bell curve is actually used a lot, okay, So I think our VC results is actually generate into a bell curve and then calculate the static score. You are the top, like, what percentage? Okay, so it's calculating that way. So this is all the shape, like following this graph, will have this bell-shaped curve, but like some curve can be fatter, can be taller, it can move to different places, but the shape is like this. And another interesting thing we can see from this bell curve, first of all, the turning point is mu, 1 over sigma over square root 2 pi. That's what it needs to remember. Why is like that? Okay, so first of all, the middle must be mu. Okay, the middle must be mu. Mu is like right in the middle. When we sketch it, we know from the graph. And also you can see if mu equals to 0. Let's have a look. If mu equals to 0, this will become 0, right? Mu minus mu is 0. So if x equals to mu, so x minus mu divided by sigma, that's 0. Then what we have is e to the power of 0, right? E to the power of 0. E to the power of 0 is 1. And then 1 times whatever in the front, that's the y value. So when x equals to mu, y equals to 1 over sigma times square root 2 pi. So that's the y value. Therefore, that's the coordinates of that point. Okay, so that's mu, 1 over sigma square root 2 pi. Okay, the x value is mu, y value is 1 over sigma times square root 2 pi. That's the first thing we can see from the bell-shaped curve. The second thing, the mean, median, and mode of normal distribution are the same, which is mu. Can we see that? This is a symmetrical curve. 50%, 50% on each side, like 0.5, 0.5 on each side, then the median must be mu. Okay, median must be mu. Mode is mu because the highest point here is mu. X value is mu. Well, also mu is the mean. Like we know mu is the mean because we said like with x is normally distributed with mu as the mean and sigma as the standard deviation. So we know already that's the mean. We can see that's the mode. We can see that's the median as well. So on the normal distribution, mean, median, mode, they are the same. Okay, mean, median, mode, they are the same. And it is mu. And the graph is symmetrical about x equals to mu. That's true, it's symmetrical about that line. Okay, it's symmetrical about x equals to mu. Many of the frequency situated near the mean. Okay, what that means? Okay, close to the mu. Can you see here? More probabilities here. Like this is large area under the curve. We have a large area under the curve here. So when we go far away, then like compared to the mean, like we have very small probability on the tail, like very small probability, and like 2 tails, and then in the middle it covers a lot of probability. How much, we'll talk about that later, but like in the middle there's more probability given a larger area, but on the 2 tails there's less probability allocated on the tail. Okay, very, very, very important thing for number 5. the graph extends infinitely to the left and left of the right and left of the mean, but never touches or go below the x-axis. This graph has it's not a hybrid function, it's just one function because the domain is R. Okay, the domain for this graph is R. And then it's same as the exponential one. I'm not sure if you remember, like there's one exponential question we did, like I said, the area at altogether end of the curve is just 1 because e to the power of negative infinity is almost 0, so we treat this area as 1. So similar reason here, even though we extend forever to each side, but because it's keep decreasing, almost like reaching 0 in the end. So that's why the overall area adding together is actually 1. So if we go integral negative infinity to positive infinity of 1 over sigma square root 2 pi times e to the power of negative a half x minus mu over sigma squared dx. If I can use calculator to anti-diff that, I should have 1. So 1 should equal to this. So the overall area under this curve from negative infinity to positive infinity actually gives you 1. Okay, actually gives you 1. So to make this become a density function, you must have domain R. Okay, you must have domain R. If domain is not R, then we don't have area 1, like it's less than 1. Okay, so we must have domain R. In other words, we ignore the practical domain. Use R instead. This is very, very, very important. Okay, so what do I mean by ignore the practical domain? Remember the example I gave you at the beginning of the class. I said mu and standard deviation will be given in the question. So I'll say the 16-year-old girl, like the height of 16-year-old girl is normally distributed with a mean of 160 centimeters and a standard deviation of 2 centimeters. Well, think about the height of a 16-year-old like girl, like maybe I'll say from 140 to maybe if not 140, like I can have some extreme case, maybe 1 meter. From 1 meter to 2 meters, that's like the possible range. But absolutely can't go below than 0, right? The height is absolutely not going to go below than 0 or not going to go above than 3 meters. Like I think no one's over 3 meters so far. So can't go over than 3 meters. This is my practical domain. I'll say make as large as possible. My practical domain should be from 0 to 300 centimeters. Like that's all the possible value I can achieve. But because we put under normal distribution already, then we need to assume what? We need to assume the girl can take any height between negative infinity to positive infinity. We do not restrict the domain only from 0 to 1, it's like 300 now. So, but there's another thing. If I can sketch, I said this is a normal distribution. This is a normal distribution with mean of 160. So here is 160, like because it's a normal distribution, height is 160. Standard deviation is 2. Okay, standard deviation is 2. So that's 158 minus 4, 156 plus 4, 164. Can you tell me what's the approximate probability here? We have learned that in chapter 13. I have like mu equals to 160 and standard deviation equals to 2 centimeters. And I have add 2 standard deviation on the left and on the right. So what's the probability for that? Sorry, what's that? 95. It's approximately 95%. Remember, like from the mu, go left and right to standard deviations, I will have approximately 95% of the data like under the curve. So it's approximately 95. Therefore, if you think about that, say 300 is here. How many distributions are there in the middle? A lot, right? 160 to 300. There's a lot of standard deviation in between. So what's the area here? It's very, very, very tiny. Okay, it's very tiny after 300. And same as 0. Where's my 0? Or not say 0. Let's say you can't really go below than 50 centimeters. Let's say 50. 160 to 50, there's 110 difference in between. So it's about the really tail part, like really, really far away from the mean. So it's very, very tiny here as well. So maybe 0.000000001, something like that for this bit and this bit. When something probability is 0.0000001, what you will say? What do you say to that probability? Is that possible to happen, or likely to happen, or very unlikely to happen, or almost impossible? It's almost impossible, right? Probably so small. So even though we take the domain for everything, but you can see after out of the practical domain, the probability becomes so small, like it's not really making any difference, like you include them or exclude them. But like to make the function to be true, we still need to include negative infinity to positive infinity. But all what I want to show here is the tail probability after the practical domain is almost impossible to happen anyway, when you calculate it on the calculator or by anyway. Like we find that can be 0.00001. So it doesn't really make any difference. Okay, it doesn't really make any difference. Even you think, oh my God, how I can take probability that's not like height below 0 or above 300? You can't take them because it's impossible. Like on your probability diagram, you can see it's almost impossible. So it's no influence. Okay, even though you change your domain to R, ignore the practical domain, but it's not going to make a big difference. Okay. This will come back again and again and again, and you will make like similar mistakes in later exercise. I believe that. But when you see normal distribution, you just tell yourself the domain is R. Okay, if I want to calculate probability x greater than 5 is 5 to infinity. You don't think about your practical domain. You don't say, oh, I can only reach 10, like then I will say 5 to 10. No, you don't set to 10. You go 5 to infinity. If you say probably x less than 160 is negative infinity to 160, not 0 to 160. So you don't restrict the most left-hand side and most right-hand side. You always take negative infinity to positive infinity. Okay, that's what I want to say. Okay, now we can say a really fantastic thing. For a normal distribution, x is normally distributed by mean mu standard deviation sigma, then variance sigma squared. For such a distribution, I have density function as indicated above. That's my density function. And I have my mu median mode equals to mu. Mean median mode equals to mu. My variance is sigma squared and my standard deviation is sigma. That's the 5 things we want to talk about for all the distribution, right? I don't need to find them. It's given in the question. It's given in the notation already. As soon as you know that's a normal distribution and you see the notation here, you know your 5 things. Okay, you want to the 5 figures. I already worked them out. To calculate probability, it's even easy. You know, for normal density function, I need to integral the thing, like integral the function from a to b and then fx dx and then work out the probability under the curve. But for normal calculator, okay, same as binomial. How you do binomial, you can do the similar thing to a normal distribution. So I'll show you the calculator page later. But I want to say, like, the understanding for normal is important. Normal is slightly different compared to all these 3 chapters we learned before. Because the previous 3 chapters, what we focus on is how to calculate the probability, how to find the mean, how to find the median, how to find the standard deviation, mode, variance. But for this one, like all the things we're trying to work out is given in the question. I can see them already. So our focus for normal distribution is not the same as the previous 3 chapters. So we focus on something else. Okay, so we'll go through see what we're focusing on for normal. now we introduce a really important thing. Okay, it's our standard. Like we have so many normal distribution, we can change my mu to anything, can change my standard deviation to any positive number. So I will have a standard normal distribution to help me. Okay, a standard normal distribution to help me. So what's a standard normal distribution? The most original one. A standard normal distribution is we normally use the random variable z to represent. We normally use x for a random variable, like x is normally distributed. But we use z to say this is a normal distribution. It's a standard normal distribution with mu 0 and standard deviation 1. This is my standard normal distribution. So my mu is 0, my standard deviation is 1. This density function is called a standard normal distribution. So something with mu 0, normal distribution with mu 0, standard deviation 1, I call that as a standard normal distribution. I will tell you how to use them like later, not today. We have density function is fx equals to 1 over square root 2 pi e minus a half x minus 0 over 1, so it's x squared. So this is my density function. You can see it's not that complex after I sub 0 and 1 in. It's a really like simple one. Okay, it's a really simple one. So what I can see here is this is the density function for a standard normal distribution, and I have sketched a graph here. So the middle is 0, and then the asymptotes is on the x-axis. This is a standard normal distribution. Mean, median, mode is 0, variance is 1, standard deviation is 1. Okay, just something you need to remember, some special names. Okay, for mu 0, standard deviation 1, we call that as a standard normal distribution. We'll use this later. Okay, we'll use this later. Okay, see, this is the most original shape. Okay, this is the most original shape of the curve. And now when we have different mu value, we have different standard deviation value, this graph will be stretched, right? Stretched this way, moving this way, this way. So let's see how we can see from, how we can tell the mu and standard deviation from a graph. Okay, from a graph. Okay, parameters mu and sigma has an effect on the normal curve. Mu controls the position of the curve. Okay, mu controls the position. I will say position of center. Okay, control the position. I'll say that's the position of the center. Where is your center? Sigma controls the width or stiffness or height of the curve. Well, I like the word height. Okay, so it's control the height. Well, they control everything like width, stiffness, and height. But I like to use the word height because the most obvious influence on the graph from sigma is the height. Okay, it's the most obvious one. Okay, if two graphs have the same height, which means they have the same sigma value. Okay, if they have the same height, they have the same sigma. That's why I will say mu1 equals to mu2. Then I can compare their mu value. The center for mu1 is on the left-hand side of mu2. So therefore, mu1 is less than mu2. Okay, mu1 is less than mu2. Okay, without looking at this, can you tell me, do you think a higher graph should give you a larger standard deviation or a shorter graph should give you a higher standard deviation? Think about the turning point we have on the first page. Think about how the sigma will change the y value. What's the turning point? Like, what's the turning point here? Mu, comma, 1 over sigma square root 2 pi, right? That's the turning point we have here. I have explained how we get that point. So when we increase the sigma value, what's the total overall change for the y value? Increase or decrease? When I increase sigma changed from 2 to 3. Do you think the overall value increase or decrease? Decrease, okay, decrease. Larger denominator will have a smaller overall value. Okay, 1 over 2, 1 over 3. So 1 over 2 is larger than 1 over 3. So increase in sigma will have decrease effect on the overall value here. So larger sigma will give you a shorter graph. Okay, a larger sigma value will give you a shorter graph. So now you can see the blue graph and the red graph. Sigma 2 is shorter than sigma 1. So therefore, sigma 2 is a larger standard deviation. Okay, sigma 2 is larger than sigma 1. So you can see from the height and to tell which sigma is larger, okay, which standard deviation is larger. The shorter the graph, like the larger, the shorter the graph, the larger the standard deviation value. Okay, let's think about transformation. Well, a standard normal distribution looks like this, okay? It's a very thin graph, like from this way. But then we can transfer like to the blue one or transfer to the red one. Well, it could happen. It's just stretch it this way, make it shorter, and then move it. So it's possible to happen. So now what we're trying to see is what's the transformation applied to the standard normal distribution? To the standard normal distribution, to transform the graph to a normal distribution with mean mu and standard deviation sigma. So my question is, I have a standard normal distribution graph like this. How this can become this graph? Okay, how this graph can become this graph? Well, it's a little bit revision on transformation now. Right. Let's back to this question here. If I say this is a standard normal distribution, what's the area under the curve? What's the area under the curve? This is a density function. What's the area under the curve? 1, right? 1. Okay, if I stretch it 2 times, by a dilation factor of 2 from the y-axis, what I should do as well? If I dilate this by 2 times from the y-axis, what I need to do as well? Dilate by a half from the x-axis, right? So because the area needs to keep as 1, so if I stretch it 2 this way, which means the area becomes 2, then it's not going to work. So I need to decrease it this way. Okay, then when we know this, let's talk about the transformation from a standard normal to just a normal distribution, mu and sigma squared. So if I have my density function here, I will say my fx equals to 1 over square root 2 pi times e to the power of negative a half x squared. Okay, this is my standard normal distribution density function. And I can say this one is fx equal, well, instead of using fx, I will use y. It's easier to use y. Okay, y equals to that. This one is 1 over sigma square root 2 pi e to the power of negative a half x minus mu over sigma squared. well, just copy the two formulas, okay? If you forget that, you can see the first page, you have that at the very beginning. That's just the two formulas. Because the right-hand side one is the new function, so I'll put dash and dash here. Okay, so it's y dash x dash. Alright, so what we will do is, well, transformation, I need to only keep the rule on the right hand side. Any coefficient, anything adding or subtracting needs to move to the y side. So what I will have here is square root 2 pi times y equals to e to the power of negative a half x squared. On this side, I will have sigma square root 2 pi times y dash equals to e to the power of negative a half x dash minus mu over sigma squared. On left hand side, right hand side is all negative a half something squared, negative a half something squared. So that's the same format already. Then I will equalize two sides. X equals to x dash minus mu over sigma. Okay, equalize the y side and equalize the x side. What I can see, y dash equals to, well, root pi is on that side, 1 over sigma times y. For the x dash side is sigma times x plus mu. There's not really reflection, like it's just dilation and translation. So I can say first dilation by a factor of 1 over sigma from the x-axis, and dilation by a factor of sigma from the y-axis. Well, can you see that that's the two steps? If you dilate from x, you must dilate from y by 1 over that factor. Because if you stretch it this way, then you need to compress it this way. If you compress this way, you need to stretch it this way. So you need to make the balance and make the area back to 1. So that's why I must have two dilations. One is from the x side and one is from the y side. And the two factor must be 1 over the other. Okay, it's the reciprocal of the other. So if one is 2, the other must be a half. If one is 5, the other is 1/5. So to make the area back to 1. And then we'll say translate. I put an absolute sign here. Mu units to the, well, to the left or right. Well, this one is mu less than 0, and this one is mu greater than 0. It depends on mu is positive or negative. Right? Depends on mu is positive or negative. If mu is negative, say it's -3, then it's moved 3 units to the left. If mu is 5, then it's moved to the right by 5 units. Okay, so this is from the easy form to the complex form. Okay, I do 3 steps. Dilation by 1 over sigma from x, sigma from the y, and then move like left or right, depends on the mu. If I say from the complex one, move to the easy one, you just go backwards order, right? You just go backwards order. If mu is originally moved to the right, then you will say it's moved to the left. Then dilation by a factor of 1 over sigma from the y-axis, and then dilation by sigma from the x-axis. You need to go backwards. If you go to page... Where's the question? There's a question, yeah, like page 5B. Okay, well, let's not look at A yet. Just think about that. State the transformation required to convert a normal distribution y equals fx to a standard normal distribution graph. It's exactly the same type of question compared to the first one. So what I want to do is I want to convert this kind of graph back to a standard normal distribution with 0 and 1. Now I want to move this back to this. So what I will have on this side is sigma times square root 2 pi times y equals to e to the power of negative a half x minus mu over sigma squared. On the other side is square root 2 pi y dash equal, that's the new graph now, to the e to the power of negative a half bracket x dash to the power of 2. Okay, negative a half x dash to the power of 2. Exactly the same as before, we just change the complex one into the front and then the easy one to the back, and then we'll put dash on the easy one because that's the new function. I want to transfer from that to that. We can equalize the same thing. Exactly same way we can do this. So it's easy to rearrange because it's already in the rearranged form. Then x minus mu over sigma equals to x dash. So x dash equals to 1 over sigma x minus mu. Okay, x minus mu is in the bracket. X minus mu is in the bracket. But I can expand, or I can describe translation first and then dilation, or I can expand it to describe dilation first and then translation. I can say x dash equals to 1 over sigma x minus mu over sigma. I can describe dilation by dilation 1 over sigma first and then translation mu over sigma. So what I will do, I will use this one. Okay, I will use this one. Okay, I will use this too. So is a translation by mu units to the left or right. If it's left, it's mu greater than 0, because if it's greater than 0, it's x minus 1, then it's minus 1, it's moving to the left. Okay, when mu is greater than 0, it's moved to the left. When mu is less than 0, it's moving to the right. For example, mu is negative 2, then mu plus 2, then mu plus 2. You just set a number in. If it's x plus 1, it's moving to the right. Okay, by 1 unit. If it's x minus 1, then it's moving to the left by 1 unit. So it depends on the mu value. Mu is positive 1, then the equation is x minus 1, then it's moving to the left. If mu is negative 1, then the equation becomes x plus 1, then it's moving to the right. Okay, it depends on the mu positive or negative, but it's opposite. then we can say there's a dilation by a factor of 1 over sigma from the y-axis and sigma from the x-axis. Okay, so 1 over sigma change to x, so it's from the y-x-axis, and then sigma from the x-axis. You can see it's totally opposite compared to what we did at the beginning. It's totally like opposite compared to what we did at the beginning. And then whatever, like what's the mu value, you just sub the mu value and sigma value in. You can just describe it later. But that's the two transformations, how the standard normal can transform to like a complex one, and how a complex one can transfer back into the standard normal distribution. So that's all we will learn for today. Okay, so I think normal is easy, hard to explain at the beginning. When you get what is normal, what all of that means, it's very easy to do the calculation actually. So we will stop here. So think about the turning point. Remember the turning point, trying to remember the density function, trying to remember what's mu, standard deviation, mean, median, like that, all the same. What's a standard normal distribution? From a graph, how you can tell like that got a higher mean or like lower mean, a higher standard deviation or lower standard deviation, and how we can apply the transformation from standard normal to a complex one and a complex one back to a standard normal. Okay, so just have a bit think about that, and tomorrow we'll continue for that. Any questions? No, that's good.